Hey! Greetings and welcome, friends. Yes. Also, enemies, I will teach you math temporarily, but you better not use it for evil. Here we go. Today we're talking about factoring special patterns. We are continuing our look at these, where we are factoring perfect square trinomials, right? Previously, we were factoring differences of squares, the a squared minus b squared pattern. And today we are talking about a trinomial, so that means three terms. Notice a 1, 2, 3, three terms. And the way you recognize this pattern is that the first term is a perfect square, the last term is a perfect square, and the middle term has to be twice the a and the b. Now, we were doing some experimentation with algebra tiles a moment ago, and we ended up realizing that the middle term had to be twice the side length of a square of this last term. But it turns out the pattern's a little bit more advanced than that. It's twice the side length of the first square and the side length of the last square. All right, so it's a little bit different, but you'll see the same idea in play. I don't actually memorize this formula twice, by the way. I memorize it once. And the version I remember is the one where I just call it plus or minus 2ab, and I make this a plus or minus is what I do. So when this factors, it's going to be a plus b times a plus b, or a plus b all squared, because multiplying something by itself is the same as squaring it. All right, so as far as how this works, all right, I suspect this might be a pattern. This was actually one of the ones that we had just had up on our algebra tiles a moment ago. I suspect this might be a pattern because the first number is a perfect square. And my question is, what would a have been if a squared is equal to n squared? A would have been the n. And the last number, I believe, is a perfect square. What would b have been in order for b squared to be 16? What squared is 16? 4, right? That's the same as me asking the question, what is the side length of the square whose area is 16, right? Or when I arranged those 16 little tiles into a square, what was the side length? We said 4. But now, I can't just use the pattern yet. I can't just say n plus 4 all squared until I need to verify this middle term. I need to ask the question, is 2ab equal to 8n? Question mark. All right, I need to make sure that the middle is equal to, right, twice the side length of this, is kind of what we had described it on the algebra tile version. So let's check that. Is 2 times n times 4 equal to 8n? Yeah, 8n equals 8n. Yes. And so without doing that, I cannot use that pattern, all right? I need to verify. This is like the final verification, authentication before I say initiate pattern sequence. And the pattern we're using is a plus b all squared. It's plus because this is a plus sign. So I'm going to say n plus 4 all squared, which, by the way, is the same as n plus 4 times n plus 4. Right, but we're going to leave it in the squared version of it. Okay, so for this, part B, the question I ask when I become suspicious of this matching a pattern and then not having to use the full AC method, which is a lot of work, is when I realize, wait a minute, this is a perfect square. And this is a perfect square. And then I ask, what would A have been and what would B have been? So A would have been 2x. B would have been 3, right? And then the question is the middle equal to 2ab? So is 2ab equal to 12x? And notice I'm completely ignoring the sign for now. All right, so is 2 times 2x times 3 equal to 12x? 2 times 2 is 4. 4 times 3 is 12. Well, yeah, it worked out. 12x equals 12x. What's wrong? I'm ignoring the sign for the moment. The only thing the sign is going to do is this next part, because this is a minus sign, the a squared minus 2ab plus b squared will equal a minus b all squared. And in my case, instead of a and b, I'm going to write 2x and 3. So I'll have 2x minus 3 all squared. All right, so let's keep trying some of these. We're gonna practice a few, and these ones I'm gonna do even quickaroo. All right, quickaroo. Here we go. Yeah, we'll do these. Yeah, sometimes it's a lot of practice is required for our brains to recognize the pattern, and then we're just like, I'm good to go. All right, so is the first term a perfect square? Yeah, a would have equaled m. Is the last term a perfect square? Yeah, 1 squared is 1. Now the question is 2ab equal to 2m? Question mark, right? Is the middle equal to 2ab? All right, so 2 times m times 1, is that equal to 2m? Yes! I don't think I need to write the third part. Yeah, just keep tracking for now, and we'll walk you through it during the class quest as well. So let's see, plug it in the pattern. It's going to be, because this is the minus sign, what's the pattern I'm using? Let's write that down. So a squared plus or minus 2ab plus b squared is equal to a plus or minus b all squared. All right, and because this is minus, I'm choosing minus here and minus there. So I'm using the minus pattern. So it's going to be a minus b all squared, which for us is going to be m minus 1 all squared. Boop. Let's see, so here, a would have been d, because d squared is d squared. B would have been what number? What squared is 25? 5. And the question is, I can't just use this pattern yet until I need to verify this middle term. Is 2ab equal to 10d? Question mark. So let's plug it in. Is 2 times d times 5 equal to 10d? And 2 times 5 is 10 times... Yeah, it works out. Cha-ching! So therefore, let's see, this is a minus sign. So I'm using the minus pattern. It's going to be a minus b, a minus 5, all squared. So, factored. Ooh, this last one is interesting. Huh. Wow, this last one's really good. We'll do this 2 different ways. All right. Wow. I'm pumped about this problem. Are you guys? Fine. Man, I am. I'm excited. All right. The reason is because we're going to do this 2 different ways. So, is the first term a perfect square? What would a have been? 3 for the 9, right? 3 squared is 9, and z for the z squared. And what would b have been? Square root of 36 is 6, right? That's the side length of the square that has 36 little tiles in it, right? Is 6. It's a 6 by 6. And now the question is 2ab equal question mark to 36z? Let's see. 2 times 3z times 6. Is that equal to 36z? Let's think this out. 2 times 3 is 6, and 6 times 6 is 36. And then there's the z. Yeah, it worked out. Right? And now that's the weird thing with math books is, right, they show you a pattern or they show you a process, and then every single problem they show you works with that process, okay? That's not always the case, just so you're aware. All right, there will be cases in which this will not work. Like if this was a 35z or a 37z, then I can't use the pattern. I would have had to try to factor different ways if it's factorable at all. Now, because this is a plus sign, I'm going to use the plus formula, plus pattern, right? So make sure you're taking note of that. So it's going to be a plus b all squared. So that's going to be 3z plus 6 all squared. Now what's interesting is this said factor, and this is actually not fully factored. Whew. Turns out I could yoink yoink from this. Well, that is part of the culture of mathematics, is that when it says factor, it wants us to factor all the way. Like, kind of like if I said simplify the fraction, we need to simplify the fraction completely. All right, between 3 and 6, I could factor out a 3. And this is weird because it's inside of a square, but I'll show you. So let's say I've got 3 times... All right, I'm going to use the square brackets. I was going to avoid it, but whatever. 3 times what is 3z? Well, that would have been 3z. And 3 times what is 6? 3 times 3 is 6? 3 times 2 is 6. All right, and then if I, because this is multiplication here, 3 squared is 9, and z plus 2 all squared is z plus 2 all squared. This is actually the fully factored form of that. It's weird, I realize. But let me show you the other thing that you could have realized that would have made that problem a little bit easier, perhaps. Whoop. Let's see, I'm going to do it over here. You might not have space, and that's okay. All right, I could have, see this 9 here? That means that the original problem I must have been able to steal a 9 from, and that is, in fact, the case. Yoink, right? I can steal the 9. So 9 times z squared plus 9 times what is 36 is 4. I could have factored the 9 out first, which is what I would recommend. Always do the GCF first if you can, because it makes all your numbers smaller. Yes. And notice that the inside of this is actually still a pattern. So A would have been, oop. Come on, give it back. No, my undo didn't undo it. Back. There we go. All right. A would have been Z, right? Z squared is Z squared. B would have been what number? What squared is 4? What's the side length of a square whose area is 4? 2, right? 2 squared is 4. And is the middle, is 2AB equal to 4Z? 2 times Z times this other thing that looks like a Z, but it's a 2. Yeah, that works out. 4Z. Bam. So, I'm going to have this 9 on the outside. This is the plus pattern, and it's going to be A plus B, Z plus 2 all squared. And notice, I get the same thing as over here. Same thing. All right, so when possible, factor out first, because it'll be easier. It'll be easier, right? So I could have made all these numbers smaller by factoring it out first. Let's see, I'll do this last problem 12, so I'm going to skip one here. All right, so this is monitoring progress question 12. Wait a minute, it's got an equal sign in it, friends. So I've got to set it equal to 0, which is already done. I've now got to factor it and then use the 0 product property. Wait a minute, I suspect this is a pattern. So A would have been A, that's convenient. And B would have been what? 3. And the question is 2 times A times 3 equal to 6A? Right, I started skipping that top line. I kept writing 2AB equals 6A, but I think you're recognizing that's what we're doing here. And I get 6A equals 6A. Cha-ching. So let's pattern this. So I'm going to have, this is the plus. So it's going to be A plus B all squared. So A plus 3 all squared equals 0. Now, what does it mean to square something? It means to multiply it by itself. So I want to point out that's the same. You don't have to write this step, but that's the same as a plus 3 times a plus 3 equals 0. And then according to the zero product property, because these two things multiply to be 0, either a plus 3 equals 0 or a plus 3 equals 0. Those are definitely not the same. And then I solve, and I really only have to solve one because hopefully you realize those are the same. And so this one actually only has one solution, which is interesting. One solution. A quadratic equation with one solution. We're going to look at the graph of this type of problem next chapter, and that's interesting. So far, all of our quadratics have had two solutions, but it is possible for the same solution to occur twice, which I think, actually, no, we did talk about that earlier. That's when we have repeated roots was the terminology that we used. Let's see. For sake of time, I think I'm done. Have a good day, friends. Bye-bye.